All right. Uh, so 10.5 is another look at conic sections, and this is something that maybe you haven't seen before. But it has to do with sort of a more algebraic interpretation of conic sections. So in 10.4 we looked at conic sections sort of geometrically as, sets of points in a plane that were defined in different ways. Algebraically speaking, though, a conic section is the graph of a second-degree equation in two variables. What does that mean? Well, a second-degree equation in two variables is one in which the degree of each term is no more than 2. Like Cindy Lou Who. The degree of a term is the sum of the exponents of the variables of the term. So the general form of the equation of a conic section is going to be something times x squared, right, degree 2, plus something times xy, right, that has degree 2 because it's 1 plus 1 is 2. Something times y squared, degree 2, right, something times x, degree 1, something times y, degree 1, and then just something else, degree 0, right, equals 0. So this is the general form of a conic section, algebraically speaking. So when you look at conic sections in this way, the really kind of thing that sticks out is this bxy term. This is called the cross product term. And this thing, we're not sure what that does. Well, we're not sure yet what that does to the conic section. It turns out to be actually a rotation of axes. But anyway, but before we get there, I just want to talk about, well, if the equation is given to you in this format rather than in the sort of graphing format that we like, what do? Well, in that case, what we do is we can get the conic in standard form by completing the square. When I say standard form, I mean sort of like the graphing form. This thing right here is the general form. So we can get it from general form to standard form by completing the square. By the way, you can get some degenerate conics, like if a, b, and c are all 0, then you just get a straight line, which is a degenerate conic. Actually, your textbook has a pretty good image of this. But anyway, let's just practice. So like here's an equation of a conic section. You know that it's a conic section because it is a degree 2 polynomial in two variables. Okay, it's a second degree equation. And so we know that it's a conic section, but it doesn't, at first glance, this is not something that we can just graph, right? In order to get it into a form that we can graph it, we need to complete the square. And if you haven't seen this trick before, I mean, I would assume most of you probably have seen this trick, but here's what you do. You group your x's together, in this case, 32x squared minus 512x. You group your y's together, 18y squared plus 180y. You move the constant term over to the other side. Okay? Then you factor out the coefficient on your x squared term and on your y squared term. So in this case, I'm going to factor out the 32. That'll leave me with an x squared. Let's see, 512 divided by 32 is 16. So x squared minus 16x, and then leave yourself some space so you can complete the square. Over here I'm going to factor out an 18, and it'll leave me with the y squared plus 10y. Again, leave some space to complete the square. And then you complete the square. To complete the square, you take the middle term, divide it by 2, and then square the result. So 16 divided by 2 is 8, and 8 squared is 64. So I'm going to add 64 here. Now, I don't get to do that for free, right? I need to balance it on the other side. So by adding a 64 inside of this set of parentheses, I'm really adding 32 times 64, which is 2048. Okay? And then in here, I do the same thing. 10 divided by 2 is 5. 5 squared is 25. By adding a 25 inside of there, I'm really adding a 25 times 18, which is 450. Okay. And now this becomes 32 times, this is just x minus 8 squared plus 18 times, this is y plus 5 squared, and that equals, I don't know, negative 2210 plus 2048 plus 450 is 288. And so we're almost there. The last thing we need to do is get a 1 here, which means we need to divide through by 288. So if I divide through by 288, 32 over 288 is 1/9. So this is going to be x minus 8 squared over 9 plus 18 divided by 288 is 1 over 16. So this would be y plus 5 squared over 16 equals 1. So there it is in its graphing form. This is an ellipse, right? With center 8, negative 5. M is 3, N is 4. All right, so you can graph that thing easily now. Let's do this again with this kind of thing. Notice that on this one, you don't have an X group to complete the square on. You just have a Y group to complete the square on. So I'm just going to group the Y's together, y squared plus 10y, and move everything else over. And then I can complete the square. Ooh, negative 16 plus 25 is 9, right? So that turned out pretty nicely. Although I don't need it to be a perfect square. Negative 16 plus 25, yeah, is 9. Okay. So then we have y plus 5 squared equals x plus 9, and there it is. This is a parabola. It's a parabola with vertex negative 9, negative 5. And it's an x equals y squared. It's positive, so it's going to open right. So you can graph that thing really easily as well. Okay, so that's how those things work. Okay, but what do you do if there is a bxy term, right? What do you do if this cross product term is there? Well, the bxy turns out to be a rotation of axes. And we can eliminate the term by rotating the axes. So here's the result. I'll give you the result, and then I'll show you some examples, right? This is theorem 10.5.1 in your textbook. If a conic section has the equation ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0, where b does not equal 0, okay, so you have the cross product term, and if an x prime y prime coordinate system is obtained by rotating the xy axes through an acute angle theta satisfying cotangent theta equals a minus c over b, that should be a capital B, a minus c over b, then in x prime y prime coordinates, the conic section will have the form a prime x prime squared plus c prime y prime squared plus d prime x prime plus e prime y prime plus f prime equals 0. Notice that there is no bxy term or b prime x prime y prime term, right? So you've eliminated it. So the question though is, what rotation does the trick? So you need the rotation, you need theta to be an acute angle that satisfies cotangent 2 theta equals a minus c over b. And then how do you get the x prime and y prime coordinates? Well, once we know what theta is, the replacements that we make are these, right? X is cosine theta x prime minus sine theta y prime. And y is sine theta x prime plus cosine theta y prime. Okay, the proof of this fact can be found on page 658 of your textbook. The top half of page 657 is also a good read if you're trying to understand where all this stuff comes from. Okay, And then sometimes it's useful to solve for x prime and y prime. And so instead of solving a system of equations every time, I'm just giving you the result that x prime is going to be x cosine theta plus y sine theta, and y prime is going to be negative x sine theta plus y cosine theta. Okay. Okay, give me a second. Okay. So here's how we would. Here are the steps that we would take to eliminate an xy term by rotation of axes. Okay. So to convert this thing to this thing, wherein we have eliminated the xy term, first of all, we find the angle of rotation theta by using the formula cotangent 2 theta equals a minus c over b. Remember that theta should be acute. That's not how you spell acute. Theta should be acute. So theta has to be in quadrant 1. Then we're going to want to find the exact values of cosine theta and sine theta. Since theta is in quadrant 1, it must be the case that 2 theta is in quadrant 1 or 2 theta is in quadrant 2. And the double angle identity cotangent 2 theta equals 2 cosine squared theta minus 1 might come in handy here. Okay. And then finally, you're going to convert from xy coordinates to x prime y prime coordinates by using these replacements. So everywhere in your equation that you see an x, you're going to replace it with cosine theta x prime minus sine theta y prime. And everywhere you see y, you're going to replace it with sine theta x prime plus cosine theta y prime. And then you have to simplify, and that usually requires some work. But let me give you a couple examples to kind of build up to it, and then I'll give you a couple of full-blown examples where we take the thing from start to finish. So number 2 here says, suppose that the axes of an xy coordinate system are rotated through an angle of theta equals 45 degrees to obtain an x prime y prime coordinate system. Find the equation of the curve x squared minus xy plus y squared minus 6 equals 0 in x prime y prime coordinates. Okay, well, I didn't give us very much space, so I'm going to cram in a little bit of work up here. If theta is 45 degrees, then sine theta equals cosine theta equals root 2 over 2, right? Because sine of 45 degrees is root 2 over 2. So everywhere I see an x in this equation, I'm going to replace it with root 2 over 2 x prime minus root 2 over 2 y prime. And everywhere I see a y, I'm going to replace it with root 2 over 2 x prime plus root 2 over 2 y prime. This is the result. Right? So I'm going to have x squared minus x times y plus y squared minus 6 equals 0. And then I've got to simplify that bad boy. Now, root 2 over 2 times root 2 over 2 is going to be 2 over 4, or in other words, 1/2. So when I square this, I'm going to have 1/2 x prime squared. I'll have a 1/2 x prime y prime, and then another 1/2 x prime y prime. So that's just going to be minus x prime y prime. And then plus 1/2 y prime squared. Here, the x prime y primes are going to cancel. So I'm just going to have a 1/2 x prime squared minus a 1/2 y prime squared. But I'm going to be subtracting it. So it's going to be minus 1/2 x prime squared plus 1/2 y prime squared. Okay, that takes care of that one. And now this one is going to be plus 1/2 x prime squared plus x prime y prime plus 1/2 y prime squared minus 6 equals 0. And then we can collect like terms. So this one and that one will cancel, but then I've got another 1/2 x prime squared there. So that gives me 1/2 x prime squared. We've got a negative x prime y prime here, and a positive x prime y prime there, so those cancel. And I don't have any x prime y prime terms left, which is exactly the goal, right? So I'm happy about that. I have a 1/2 y prime squared, another 1/2 y prime squared, and another 1/2 y prime squared. So I'm going to have in total 3/2 y prime squared, and then minus 6 equals 0. Okay, so I've done it, right? This is as good as it gets, but well, it's not as good as it gets, but this is given now in x prime y prime coordinates. If I wanted to be able to identify this thing, I would need to go a few steps further. It looks like an ellipse for sure, but an ellipse has equation, something x squared plus something y squared equals 1. So I need to move the 6 over and then divide through by 6. So I'm going to have x prime squared over 2 plus, we can say y prime squared over 2/3, right? 3/2 times that is the same as dividing by 2/3 equals 6. And then I can divide through by 6, which is the same as multiplying the denominators by 6. So I would get x prime squared over 12 plus y prime squared over 3 would cancel, 3 leaves, so over 4 equals 1. And there's our beautiful ellipse. To graph this thing now, what you would do is, and we weren't asked to do this, but just to kind of drive the point home, you would take this original coordinate system and rotate the axes 45 degrees. Right? And then you would graph this equation relative to this new axis system, right? So it would be centered at 0, 0. You'd go left and right root 12, which is like, I don't know, whatever it is. And then you do that, and then you get, this kind of an ellipse. And then when you view that with respect to the original axis, it looks like an ellipse that's been tilted onto its side. Anyway, so that's the idea. For some reason, my printer didn't print page 3, so I had to write these ones out by hand, but that's okay. So number 3 says, find the new coordinates of the point 2, 4 if the coordinate axes are rotated through an angle of theta equals 30 degrees. Okay, so this is where I would use this other formulation, because I'm given the x, y coordinates, so I know what x and y are, and I want to figure out what x prime and y prime are. So I would use this other kind of formulation for x prime and y prime. I'd say, right, because here you know what x prime and y prime are, and you want to find x and y. You want to rewrite x and y in terms of x prime and y prime. Here we want to rewrite x prime and y prime in terms of x and y. But anyway, x prime is going to be x cosine theta plus y sine theta. It's very similar. And y prime is going to be negative x sine theta plus y cosine theta. Again, very similar. Well, so first of all, let me just say cosine theta. So cosine of 30 degrees is root 3 over 2. And sine theta, right, sine of 30 degrees would be 1/2. Okay? So x prime is going to be x cosine theta. So that's 2, right? Because there's x and there's y. So it's going to be 2 times cosine theta plus y times sine theta. So that's going to, the 2's will cancel, you get root 3. Here the 2's cancel and leave a 2. You're left with a 2. So you get root 3 plus 2 for x prime. For y prime is going to be negative x sine theta. So negative x sine theta plus y cosine theta. And that's going to be negative 1 plus 2 root 3 for y prime. Okay. Putting that together, the point that you get in x prime, y prime coordinates would be 2 plus root 3, comma, 2 root 3 minus 1. There's the x prime, y prime coordinates. Okay, I've got to rescue a child. Okay, well, she's still crying a little bit in the background, but hopefully it's not too much of a distraction. Okay, so finally, let's actually sketch some of these curves. I mean, I know on the example on the previous page I kind of did one of them already, but I didn't do it very neatly. So let's see if we can actually identify and sketch some of these curves. And this time we're not given the angle of rotation. Our task is to find that out ourselves. So here we go. So first of all, we need to find the angle of rotation theta, and that angle has to satisfy the equation cotangent to theta has to equal a minus c over b. Did I get that right? Yep, cotangent to theta equals a minus c over b. That would be 5 minus, in this case, 5 minus 5 over negative 8, which is just 0. So if cotangent to theta equals 0, and also remember theta is an acute angle. So if cotangent to theta equals 0, when is cotangent equal to 0? Cotangent is equal to 0 at pi over 2. So 2 theta equals pi over 2. And that means theta equals pi over 4. Okay, well that's good to know because now we can say sine theta and cosine theta are both going to be root 2 over 2, right? So sine theta equals cosine theta equals root 2 over 2 in this case. That's good to know because now we're going to go to our equation, and everywhere we see an x, we're going to replace it with root 2 over 2x prime minus root 2 over 2y prime. And everywhere we see a y, we're going to replace it with root 2 over 2x prime plus root 2 over 2y prime. And I know we did a similar thing in number 2, so you might be thinking, well, it's always root 2 over 2. It's not. It's not. Theta could be something different from pi over 4, right? But anyway, so let's do it. We're going to have 5 times x cosine theta x prime minus root 2 over 2 y prime squared. So there's 5x squared minus 8 times x times y plus 5 times y squared minus 9 equals 0. Okay. So this is going to be 5 times 1/2 x prime squared minus x prime y prime plus 1/2 y prime squared minus 8 times 1/2 x prime squared. The middle terms will cancel. Minus 1/2 y prime squared plus 5 times 1/2 x prime squared plus x prime y prime plus 1/2 y prime squared minus 9 equals 0. And let's see. So I'm going to have 5/2 x prime squared plus another 5/2 x prime squared, but minus an 8/2 x prime squared. So that's 10/2 minus 8/2, that's 2/2. So just 1 x prime squared. That gets rid of all of these. Okay, x prime y primes. I'm going to have negative 5 of them here and positive 5 of them there, so they cancel, just like we intended. y prime squared. So I'm going to have 5 halves here, another 5 halves there, that makes 10 halves, and then a positive 8 halves, so that makes 18 halves, or in other words 9 y prime squareds. This other 9 I'll move over to the other side. And this is another ellipse, isn't it? If I divide through by 9, I get x prime squared over 9 plus y prime squared over 1 equals 1. Okay, so it's an ellipse. Now let's graph this thing. So to graph this thing, I'm going to take my original coordinate system and I'm going to rotate it through an angle of theta radians, so pi over 4 in this case. Or I guess it could be in degrees, right? We could have called it 45 degrees, whatever. The same thing. So I get this new coordinate system, which looks something like this. Right, so if this is my original xy coordinate system, then this is my coordinate system x prime, y prime. And I'm going to graph the ellipse centered at 0, 0. I'm going to go 3 units left and right. 1, 2, 3. So there's a vertex. 1, 2, 3. There's a vertex. And then I'm going to go 1 unit up and down. And then I'm going to draw that ellipse. And that's what I end up with. I should have done the x prime, y prime coordinates in pencil so that I could erase it, so that you could see that with respect to your original axis system, your original xy axis system, this is just an ellipse. It's an ellipse that's been rotated 45 degrees, right? So it's kind of cool. Okay, one more. Okay, so first of all, we've got to find theta. So we'll say cotangent to theta equals a minus c over b. So let's see, 32 minus 18 divided by negative 48 is negative 7/24. Okay. So I may not be able to find theta, an exact value for theta. Of course, I could take cotangent inverse of both sides and then divide by 2, right? That would give me the exact value of theta. But I mean, I'm not going to get like theta equals 30 degrees or something out of this. This is not one of those kinds of things that we know off the top of our heads. But what we could do is this. So we can use some trig. So cotangent is adjacent over opposite. That's x over y. So you know x is negative 7 and y is positive 24. Right? So there's 2 theta right there. And then we can solve for the hypotenuse, right? So 7 squared plus 24 squared is 625. Square root of 625 is 25. Oh, of course, right? 7, 24, 20. Yeah, this is just one of those special triangles, right? So the hypotenuse is 25. That means that cosine of 2 theta is adjacent over hypotenuse, so negative 7/25. Okay, so how does that help us? Well, I'm going to use this identity right here in order to figure out the exact value of cosine theta. Okay, and once I have that, I'll be able to find the exact value of sine theta as well. Oops. Okay, so cosine 2 theta is 2 cosine squared theta minus 1. And I know that cosine 2 theta is negative 7/25. If I add 1, negative 7/25 plus 1 is 18/25. And then if I divide by 2, 18 divided by 2 is 9. So I would get cosine squared theta equals 9/25. And then I would take the square root, and technically I should have that cosine theta is plus or minus 3/5. But I know that theta is acute. I know that theta is in quadrant 1. So cosine theta is positive. So cosine theta must be 3/5. All right. If cosine theta is 3/5, then sine theta is 4/5, right? This is just a special 3, 4, 5 triangle. If you don't believe me, you can draw the triangle, label the adjacent side 3, the hypotenuse 5, solve for the opposite side, and you'll see that it's 4 using Pythagorean identity, or Pythagorean theorem. Okay, so there we go. So we know that cosine theta is 3/5 and sine theta is 4/5. Now we can use that to make the necessary replacements. Because again, we're going to replace everywhere we see an x, we're going to replace it with cosine theta x prime minus sine theta y prime. And we're going to replace all of our y's with sine theta x prime plus cosine theta y prime. So let's do that. So I'm going to have, I'm going to need to give myself space and write kind of small, but I'm going to have 32 times x squared. That's going to be cosine theta, which is 3/5, times x prime, minus sine theta, which is 4/5, times y prime. So there's x squared, minus 48 times x, times y. Y is going to be replaced with sine theta times x prime plus cosine theta times y prime. So sine theta times x prime plus cosine theta times y prime. Okay, plus 18 times y squared, that's what I just wrote down, minus 15 times x, minus 20 times y. Equals 0. Okay, somehow I managed to cram it all into that line. I should maybe zoom out if I can. Okay, and then the rest is algebra, right? I mean, so we're going to have 32 times 3/5 squared is going to be 9/25. This is 9/25 x prime squared. 3/5 times 4/5 is 12/5, but I'll have 2 copies of that, so it's going to be 24. So I'm going to say minus 24/25 x prime y prime plus 16/25 y prime squared minus 48 times 12/25 x prime squared. Then I'll have 9/25 x prime y prime minus 16/25 x prime y prime. 9 minus 16. Oh, my brain is getting tired. I couldn't do that in my head. But it was it's negative 7/25 x prime y prime. And then a negative 12/25 y prime squared. Okay. Plus 18 times. This is going to be 16/25 x prime squared. We'll have 12/25 x prime y prime, and then it'll double, so it'll be plus 24/25 x prime y prime plus 9/25 x prime squared. And then I'm going to go to the next line. Then we'll have the minus 15 times 3/5 x prime minus 4/5 y prime minus 20 times 4/5 x prime plus 3/5 y prime equals 0. Okay, now I'm going to collect all of my x prime squareds. I'm going to have 32 times 9/25. So 32 times 9/25. That's 288/25 minus 48 times 12/25 x prime squared plus 18 times 16/25. And wouldn't you know it, those just cancel off. All of my x prime squareds are gone. Okay, what about my x prime y primes? Those I really hope cancel off. So I'm going to have negative 32 times 24/25. Negative 32 times 24/25. This negative and that negative will cancel, make a positive. So I'm going to say plus 48 times 7 times 7/25. And then here, plus 18 times 24/25. That also equals 0. Thank goodness. Otherwise, I'd have to go back and figure out where my mistake was. Okay, what about my y prime squares? I'm going to have 32 times 16/25 plus 48 times 12/25, and then plus 18 times 9/25. And that comes out to 50. So I've got 50, 20, no, that just comes out to 50. Not 50/25, it's just 50. So I'm going to have 50 y prime squared. That takes care of all those guys. Now for my x primes, I'm going to have negative 15 times 3/5 minus 20 times 4/5. That comes out to negative 25. So I've got negative 25 x prime. And finally my y primes, I'm going to have a positive 15 times 4/5 minus 20 times 3/5. And that comes out to 0. So my y primes are also gone. So this thing just equals 0. Look at all look at all that cancellation, right? It's kind of beautiful. Okay, this looks like a parabola, right? If we add the 25x prime over, and then I'm just going to rearrange the order here. We can divide by 25. X prime equals 2y prime squared. So it's just a parabola, opens right. Okay. The only other thing we need to do is figure out, well, what was the angle of rotation, right? Well, it would be cosine inverse of, well, here's what we would say. Since cosine 2 theta, or actually, never mind, we've got cosine theta equals 3/5. So I'm just going to say, since cosine theta is 3/5, theta would be cosine inverse of 3/5. Cosine inverse of 3/5 is approximately let me get it in degrees. It's approximately 53.1 degrees. Okay, so that's our angle of rotation. So we're not going to rotate the axes 45 degrees, we're going to rotate them 53.1, so a little more than 45. So maybe it would look something like that. And like that. Oh, and again, I should have done it in pencil instead of pen, but oh well. This is our xy coordinate system. This is our x prime, y prime coordinate system. And we're going to graph x equals 2y squared relative to this coordinate system. Well, the vertex is 0, 0. Okay? And then this thing opens right. So now normally we would go over 1, up 1. But because this thing is being doubled, we're going to go over 1 and up 2, right? Is that right? If I plug in y equals 1, I get x equals 2. Sorry. So actually I get that point and that point. Okay? And if I plug in y equals 2, or y equals negative 2, I get 8. 1, 2, 3, 4, 5, 6, 7, 8. Well, so that's like almost off the charts, right? But something like this. Okay, so I get this kind of parabola. Okay, and so relative to my original axis system, it just looks like parabola that's been tilted. Instead of opening right, it's been tilted up 53.1 degrees. Okay, that's how we take care of these beasts.